Okay. So let's talk about the material jetting process. So the material jetting is quite similar to the inject based printing, and it is actually developed based on the 2D printer, 2D inject printing. So basically, this inject printer will selectively print a layer of liquid polymer and cure it, make it solidify. But there's no vat of polymers, different from the vat polymerization, but still utilizing the light source as the power. Oh,
Professor,
I
I
did.
think you're
Oh,
showing
I
with us now.
didn't. Sorry, I don't realize it. Yeah, just 1 second. Can you see it right now? My screen.
Yep, I can see it
Okay,
now.
good. Sorry about that. So as I mentioned, the inkjet-based process is similar to the vat polymerization, and the only difference is there's no vat, right? But still, it utilized UV light to cure the entire print area. I think we could look at a video or an illustration figure. I think there's a video next it. But let's look at the a very typical process, which is the Stratasys PolyJet process. We have a printer, Stratasys PolyJet printer at Amprint Center. I mean, hopefully we will have the chance to have a demo session on it. But it's let's look at its working principles. So basically, this printer will selectively print a layer of liquid polymer. Basically, it will spread out the liquid polymer onto the platform, and then an array of 4 inkjet printing heads scan back and forth, jetting a polymer onto the platform and cure it using the UV lamp. So there's no laser involved in this process, different from the vat polymerization. Instead, it utilized the UV lamps. That's one way in the material jetting process. Also, there are process utilizing the thermal energy. It's not a light source, but more a thermal source, energy source to cure the material. And the biggest benefit for this process is just think about what you will have if you have a 2D printer. That is, you can print the multiple color using a 2D printer, right? So in this case, we have multiple material available in the printing, which is a really nice feature. If you look at some of the prints from this Stratasys machine, it's a very realistic, high quality prints with multiple material and colors. Here shows a illustration process of the print. As you can see here, this printing had moved back and forth, and there's a light source cure the newly jetted material to the platform, right? So I mean, you can just think of this as a 2D printer, but the only thing is, it does not just move in the XY plane. It will this platform will move in the Z direction as well, such that different layers will be accumulated. That's the main idea of this material jetting process. So as you can see here, on the same prints, there could be different colors, right? And so there will be the different ways, different materials properties as well. There could be some variations. For example, 3D system has its own material jetting process called the multi-jet printing. So that's very similar to the Stratasys ones. If you look at the whole process of this polyjet printing, there are 4 steps. First, the 3D model has to be sliced into different layers. And then the material will be jetted onto the platform or the previously printed layers. And then the platform will be leveled. And then the UV light source will be utilized to cure the liquid material and make it solidified. And then another layer will be jetted later. So that, the printing platform will be moved to have to level down one layer thickness, such that you could spread another layer of material to do the to print the next layer. So that's the 5 steps of the polyjet printing process. If you take a close look of the printing head, actually there's some there's something like this. So the liquid material will go from this printing head and drop onto the printing platform. That's the picture shows this process. Basically, the liquid material will be jetted and in the scanning direction, which is the XY direction. And these liquid droplet will have a drop velocity. Basically, this is a parameter controlled by us. You could have a fast dropping speed of the droplet or a slower one. Of course, the nozzle have different diameters. For this polyjet jetting process, it's 40 microns, which is really small diameter compared to other process, right? Can you think of this 40 microns? If you look at the fused deposition modeling, we are talking about 0.4 millimeter or 0.8 millimeter. Now, with this polyjet process, is 40 micron. So that is really small compared to the fused deposition modeling, right? As I mentioned, it's similar to the 2D printing. For the 2D printing, it has such a small diameter, right? So another thing is there are quite a lot nozzles. There are 192 nozzles per channel. If you look at this figure, sorry, as you can see here, each of the small dots are from one nozzle. You can see there are massive number of nozzles jetting the material at the same time, right? Also, in total, there are 2 channels per printing head. So basically, how many nozzles you have in total? That is 1 92 times 2, which is 384 nozzles for one printing head. That's quite a lot printing, nozzles for one single printing head. And basically, if you look at it, this structure, if we look at this side, means the one is jetting the material out. What you will see is, well, you have these holes, which are the nozzles, to allow the material, liquid material, jetted onto the printing platform. And there are gaps between each of the dots. Usually there are 80 to 100 microns between each of the dots. So let's say you have a printing head 65 millimeter wide and has a 192 nozzles. So what is the y-axis drop spacing on the head? So what you wanted to compute is, well, you have this to be 95, and you have 192 nozzles. So the distance between each of these, basically you just use the 95 over 192, and that is the spacing, drop spacing on the head, because each of this hole will allow the one droplet to be jetted on the platform. So let's see, this will allow one droplet, this will allow another, and this allows another, and so on. And turns out the distance between these holes will determine the distance between this drop spaced from each other. And basically you want to use this dimensions and the number of nozzles to compute it. So another question is whether the drop spacing in the X direction have the equal drop spacing in the Y. Any idea about it? So can you think of what will be the factor to affect this drop spacing in the X? Any thoughts on it?
Would it be the rate at which the head is moving?
Exactly. Exactly. Basically, it's not equivalent to the drop spacing in the Y, because we are moving our printing head in the X-axis, right? That means how fast you move your printing head will affect this spacing. So definitely it's not equivalent to the droplet spacing in the X-axis. So let's look at it. Another step for the PolyJet printing is the leveling. So that is to level the material, to spread out the material onto the printed model, and to make sure the layer thickness can be maintained during the whole printing process. So after the material is spread out, the liquid resin will be cured with the UV lights. So this here shows you the UV light source. So it's similar to, I mean, it has the similar working principle for the curing as the VAT polymerization. So that is this light source energy, I mean, light energy will cure these polymers, make it solidify. And here shows you still the layering process. That is, you print one layer and then the platform move down and then print another one and move down and so on and so forth. Turns out you will have the whole parts printed. In this process, it requires the support. The reason is there's no natural supports. In the powder-based process, like the selective laser sintering we talked about in last lecture, the whole model are buried inside a box of powders, right? So it does not require any support material. But in this one, only the layer, only the region with only the region with the material will be cured. In that sense, for example, if you flip this trapezoid shape like this, turns out the region like here, it will require some support because the normal of this facet is pointing opposite to the Z direction, right? So that is the normal. And the Z component of this normal is pointing downward. And the printing process is pointing upward. In that sense, this region will require some support. So in this process, there will be some gel-like support material printed. And it's similar to what the fused deposition modeling does, or the VAT polymerization does. It does require the support material for these regions. And the post-processing need to be conducted. So because this kind of a support material could be washed away or dissolved using some solutions. So usually these support material will be used, will be removed in these ways. Also, there could be some other post-processing, but they are not necessary usually. Sorry. Then let's talk about the resolution of accuracy of the prints. As you can see here, we have really small spacing between each of the nozzle. That suggests we could have a relative high accurate or high resolution during the printing. So for example, if you have a 600 by 600 by 1600 resolution, so that means there will be 600 droplets per inch in both X and Y axis. And also there will be 1600 drops per inch in the Z axis, which suggests a 14 micron layer thickness. That is really accurate, really small layer thickness. In that sense, it will have a really high accuracy. But as a price you have to pay is you will have more layers for the same model, and it takes more time. But in some of these applications which requires a high resolution, high accuracy of the prints, you probably want to pay this price, right? If the accuracy is the main consideration, right? In that sense, you could probably print some of these models requires a high precise clearance. For example, the gaps between the two mating parts, right? That's possible. Basically, its tolerance is between the positive and negative 0.001 inch to 0.003 inch for a feature less than 2 inch. If you're talking about very large feature, then the tolerance will be positive and negative 0.008 inch. But still, it's a relatively smaller than the fused deposition modeling. And you will have really smooth surfaces if using the very high resolution of the prints. So if we look at the PolyJet printer, the Stratasys printer, there are different print modes. So for example, there are high-speed print. But if you talk about high speed, again, it usually suggests a larger layer thickness. So there could be 3 material used here and 3 printing head utilized. Also, there could be 2 printing head for the support materials. And then if you look at the higher quality, sorry, or the accuracy, then the layer thickness has been halved, right? And there are more material could be used and more printing head to be used. But still, only 2 printing heads for the support material. Also, that could be the high mixed. That is still the layer thickness is 28 micron, but there are more material utilized. Is there any questions? I heard someone asking question. No? Okay, all right. So the difference between this high mixed versus this high speed is there are more material could be utilized and more printing head to be utilized because each of the printing head probably has one specific material there. So that's a reason. And if you look at the zoom in view of the same parts printed using different mode, for the high speed mode, see these layer thickness is 2 times larger than this than the one on the using high quality mode, right? So that will be the difference. But again, you want to always find a balance. Make sure if you want to have a high quality, choose this high quality mode. But if you want to have a quick prototyping, probably the high speed mode is more appropriate. Basically, if you look at how people change the material, it's like a carbonate, right? And this material cartridge is inserted into this carbonate. And there are different materials this printer could use with different colors. But primarily the polymer materials. As you can see here, it can print really nice multi-material and multi-color products. And here show you the different materials. This could be used with different colors available. For these medical applications, this will be really nice machine to use. It can print very clean, very clear products with high quality, And sometimes the rigidity, if the rigidity is the main consideration, then some thermoplastic ones will be used in the printing process. So there could be some really complex multi-material object to be printed, like this human heart model. So as you can see here, there are soft regions, soft tissues. There are vacuum, vaccine, and also some of these muscles and so on and so forth. They are in different rigidity, as well as that different colors. So basically, that requires the composition of different material, different base materials. For such kind of material, there's a name, which is the digital material. That is the composition of different base model materials to achieve specific concentration and structures. That could be achieved. This kind of digital material composition could be achieved using their associated softwares. It allows some material editing by combining the available material together to have some new material properties and also structures. And after you have designed your digital material during the printing process, this will be automatically taken care by the printer without any user intervention. That's a really nice feature, right? If you use the fused deposition modeling for different materials, probably you want to print something and then pause the printer, change the material, and then continue the printing, so on and so forth. But for this one, because in the process, each the droplet will have a specific, a unique material property or color. So once you have program at each region, what will be the material? Once that is determined, during the printing process, the printer will specifically put what you planned in the modeling stage, and that will allow such kind of complex prints with multiple materials and multiple color, which is really convenient. So the multicolor is more like a, you can consider about one color is one material, right? So because it has this printing process has ability for the multiple color printing, it's by nature it has the capability to print the multiple. It has the capability to print multiple material. By nature, it has the capability to print multiple color. And as you might already know, the color could be composed by the basic colors, right? Any of the color could be considered as a combination of the base colors. And as you can see here, there's a color palette demonstrate what are the available colors to be used in the printer. Also, there could be some transparent effect for the object. For example, if you look at this, right, this region, it's semi-transparent. So here show you some of the example printed using this printing process. So as you can see, these glass lenses, which could be printed in using this process. Actually, I don't know if you were aware of some of the custom glasses companies online. So what they do is they will provide a custom glass, not only for the frames, but also for the for these lenses. I mean, although we use those standard lenses, in most of cases it works. But ideally, if everybody has a unique lens, it will achieve the best functions, right? So in that case, customize a lens for you is attractive. With this printing process, that makes things possible because it could utilize multiple material, and it utilizes this really clear material for the fabrication. And in the same printing pass, it could print different lenses for different person with different shapes. That will essentially enable a customization for the glasses, right? And also, if you look at how detailed the print could be, right? So here show you some of the processes for the support remove. So basically, you have this kind of a little region with a low pressure tap water to wash away those gel-like support material from the prints. So I don't want to go to the details about the support removal. You could check the slides, but the overall idea is to use the water to dissolve the material. Also, you could paint the model using different material, like the one shown here, right? Basically, clean the model, dry sanding it for better adhesions, and then you can file the model or apply the prime and paint it finally. So that's the standard process, like what people does for other polymer objects or plastic object. So for some of the objects like these ones, that definitely requires the some process and the paints for more realistic look. Also, the hydrographics could be another way to apply this kind of textures to these prints. Different models for one object could be glued together for a larger object. So like the one showing here, it has 26 parts, and you just want to glue them together. So in order to make the glue easier and firmly, I mean, one thing you want to do is to design such kind of features to make sure they will be locked tightly, and if you apply glue to these regions, it will be more firm than without such kind of features, the locking features. So when you consider about using glue, think of adding these features to increase the firmness. Here shows another post-processing for the prints, which is the photo bleaching. And again, that's for the appearance. You could use a table lamp to kind of photo bleach the part. And here shows you the different effect. If you have a longer time, usually the clarity will be better for the clear parts, right? Here shows you if you have some objects like this before the treatment, it's not that good. But if you have a photo bleaching in the chamfer, it will become more clear. And the table lamps gives I would say quite comparable result to the chamfers, but a slightly worse result. So if you have the chamfer, that will give you the best photo bleaching effect result for the clear product. So again, the details, you can check it yourself. So another thing is the part positioning for the prints, right? Because if you look at the prints, it will have more clear prints far from the corner, but a yellow one near the corner. That is because these corner ones have more exposure to the UV light. In that sense, it has been over cured. So if you in that case, you will have such kind of difference, the color difference. The clarity difference from here to here. And another thing is you don't want to build the small part next to the tall one. So that will again have the different, give you the different clarity due to the time of exposure to the UV light. I think we can stop here and continue the discussion of this process in the next class. Let's go back at 11:10. All right. So let's go back. So another processing is the polishing. So that is for creating smooth and clear surfaces by sanding it. As you can see here, if you have a lens like this, and you will see it's not clear, and it's not transparent enough, right? But once you have the polishing, you will see the improvement for the clarity of the part. So that's why you want to use the polishing to post-process the part. There are different ways, and basically there are dry sand surface and wet sand surface polishing, and also some micro mesh sandings. So these are the different ways of the polishing, and from the rough to fine, right? During the polish. So here show you another comparison. That's the one before and after the polishing. You can see how different it is, right? The in terms of the clarity of the parts and the smoothness. Sometimes the there are some other chemical-based method, like the dyeing translucent models. So basically, you want to use you want to have a painting of your transparent part. That is what you could do, right? Here gives you the idea how you could print it. Basically, use these chemical solutions and paint it, and it turns out you will have a in this case a red color for the original clear parts. And this castle, I think a Disney castle or Harry Potter, I'm not sure, but turns out you have a light blue color by using this method. Also, there's a liquoring process, that is applying a coat of clear liquor that will give you a shine appearance of the part, and it will protect the surface. So again, you can check the details yourself, but that's also for the appearance improvement and surface finishing improvement. Also, there is a thermal treatment. So basically, you have a furnace like this, and the model printed could be put into this furnace or oven, and turns out with some preset temperature, this material heat resistance would be increased. But you want to be very careful for the part to be thermal treated. That is, you want to have a high temperature ABS-like material. Otherwise, it will damage the parts. So that's the thermal treatment. Metal coating, like the one showing here. Basically, you have a nickel or a chrome based method, and that will coat the original model with a layer of metal, and it turns out it have this metal-like surface. And also you could do some post-processing, which is beyond this appearance or the surface finishing. You could drill holes or create other features based on what you have from the prints. As long as the material can bear the amount of forces from these processes, meaning it will not broken, right? You can safely use the drilling and tapping to create holes or to generate some hollowed regions, areas. But again, you have to be very careful to apply drilling and tapping, because some brittle material, once you have this tool to be utilized, it will immediately get broken. And that's not what you want. So be careful of this drilling process. Okay. I think that's the fundamental of the material jetting, and let's look at some not this. Let's look at the lecture 11, which is some detailed understanding of the printing, not this, the printing head, and also the printability of the ink. So the inkjet-based method, as I mentioned, there are two different working principles. One is thermal-based. Another one is piezo-based. So usually the diameter of the nozzle is like 10 microns, out of 10 microns. And there's not only one nozzle per printing head. Usually it's an array of hundreds of nozzles arranged in one or more rows. And the way, basically for the light source, you are looking at the shape of the voltage signal sent to the printing. I mean, for the controlling of the printing head, there will be a voltage signal sent, and that will control the open and close of the nozzle for the ejection of the droplet from the nozzle. Also the printing head will move at a speed. Usually it's around 1 meter per second relative to another one. The droplet velocity, basically this droplet velocity describes the droplet dropping to the platform, this velocity. And this head and platen move speed means it moves in this direction and this direction. So that's the difference. Also, the printing head is 1 millimeter above the substrate. Basically, if the printing head is here and this substrate is here, the distance between them is 1 millimeter, right? So with this height fixed, and with the droplet velocity determined, then you will know how long this droplet will fall from this printing head to the platform, right? That could be computed, right? And as I mentioned, there are two different types of the inject, the thermal one and the piezo one. So for the thermal one, what it look like? So basically, this illustration is is about the thermal inject, and it's a upside down view. Basically, here shows how where the droplet go out of this printing head. Here shows you where the ink will be filled into this ink channel. So what it does is there is a resistive heater above in these regions, like the one showing here. See, in these regions, and this heater will boil the liquid material and generate a bubble, a void region. Oh, and it turns out it will push the material out of this small slit, small hole, and form a droplet. That's how it works. So that is why it is a thermal inject, right? Basically, it utilizes the thermal energy to heat up the liquid material, generate the bubble, and push the droplet out of the small hole. And that's it. For the piezo one, it's different. So basically, the piezo material is a very special material. When the piezo material has a voltage applied, it will deform. See, these originally they are the planar layers, but after the electric voltage applied to it, it will deform to a curved shape. And because it moves in this way, it will push the liquid material out of this small hole and form a droplet. So that's what the piezoelectric inject prints work. But both of the two methods could be controlled by the voltage in different ways, right? So the electrical voltage applied to thermal, it changed the it will generate the different heat, and then that controls how fast this thermal this bubble will be produced, such that it controls the ink droplet. And similarly, the electric voltage is changed so as the deformation of the piezo transducers. And once the frequency of this deflection will affect the frequency of the droplet coming out from this hole. So that's why we can control the droplet by manipulating the voltage. Any questions so far? Okay, good. So here show you the image from this angle, different angle. Basically, this shows how the droplet travel in this z axis, and here shows you how the trace formed, or the dots forms when the droplet fall down onto the platform. So if a droplet with a low surface tension, what will this look like? If the droplet has a low surface tension, any idea?
Would it be flat?
Yeah, flat or elongated. So it will be longer in another word, right? Oh, sorry. I think I should use the eraser. So that's what it will appear if a droplet has a low surface tension. On the other hand, if a droplet has a high surface tension, it will be more round, more like dots, right? So basically that will suggest the importance of the surface tension to change the shape of the droplet. And then what is the significance of the prints of printing these droplet onto a moving platform? So one thing you definitely don't want to have is to have some low controllability of the accuracy. That means the material, the printing head jet onto the platform is not the shape you want. And essentially that will affect the accuracy of the prints. So if you have a low surface, if you have a droplet with low surface tension, what it will does is it will streak on the platform. It will have some access regions to be covered due to this streak. And it turns out that make the printing accuracy cannot be controlled well. So that suggests us if we want to have a really high precision for the prints, probably you want to maintain a sphere shape of the droplet, and that will give you a better accuracy control during the print. So that's why there are research to study how for different material and different parts in different thermal or piezo process, how the droplet could be controlled. What will be the ideal shape of the droplet? And there are some specifications for the inject head. And there are quite a bit manufacturers like the one showing here. So as you can see here, there are quite a bit overlap of this company with the 2D inject manufacturers because they really share the similar working principles for the 2D one and the 3D ones. So for example, the Stratasys use the Recon printing head, right? And 3D system use the Xerox print head. There could be quite a wide range of the printing heads from 750 to over 5,000, but still it's quite expensive. Even for the lowest price, it's expensive compared to other printing process. So one printing head has multiple components, like the number of nozzles, nozzle pitch, droplet size, droplet velocity, and the furring frequency, and also what kind of ink could be compatible for this printing head. There could be an issue for the printing head, and these are some listed ones. For example, we want to put the printing head vacuum vacuum. And the reason for it is you don't want to have the liquid oozing from the nozzle. And that's why the vacuum is necessary. Again, that will affect the controllability of your prints and essentially the accuracy of the prints. So another thing is the cappings. So what happens if you keep the printing head left in open? Can you think of any reason for a cap for the printing head? Just to think of some of the scenario for using some pens or glues. If you keep it open, what's going to happen?
Does capping prevent the ink from drying out?
Exactly. That is, if you keep it open, it turns out the ink will dry out and will stuck. The whole we'll get the printing head stuck, and it is inevitable. That means, well, this printing head cannot be used anymore. You have to purchase another one, and remember how expensive it is. See, definitely you don't want to spend that much for not capping your printing head. So that's the reason for the cappings. Of course, there are other factors you want to think of, like the straightness of the jetting, and ideally you want to have a straight line for a trace jet from the printing head. Also, the droplet velocity versus voltage, as I mentioned, that is that it has a relationship. The voltage will control the droplet velocity, and the droplet velocity will affect the printed patterns onto the substrate. And droplet volumes, that will change the geometry of the droplet, make the controllability different. That's another reason for the droplet volume. So another interesting topic is the resolution versus the drop spacing. So basically, because this drops are also in the form of a small dot. So in the 2D printing, there's a concept called the DPI, dots per inch. So that also represents the image resolution or the print's resolution. So in with the DPI, it basically measures for a given area how many dots there will be. With more dots, that means the spacing between each of the dots are smaller, and in that sense, it has a higher resolution. The printing software will allow you to specify how far apart those printed droplets will be spaced in microns. And that will essentially change the resolution as well. And when using an industry printer, basically you want to match the two numbers, or the printed image will be either larger or smaller than you expected. So in that sense, if you want to print a model with the ideal spacing, you want to also check the DPI as well for this printer could provide. So here show you the conversion of DPI versus the spacing of the dot. So if you have a 50 DPI, that means in the 1 inch, that's 1 inch. In 1 inch distance, there will be, I just draw some dots, but cannot draw all of them, but just give you some ideas. There will be 50 dots, right? Now, how to compute the spacing? Basically, you want to use 1 inch over 50, but that is the spacing in inch, and then you convert it to the micrometer or microns, right? Remember this different unit. This is inch, and this is microns. You want to do this conversion very carefully to have this finally this 508 microns. So similarly, if you have 100 DPI, that will be this spacing. You have more DPIs, larger DPIs, the spacing is smaller and smaller. So that's how you do this conversion. That could be questions given the resolution in terms of DPI, and let you compute the spacing, or give the spacing, you come up with the resolution, right? Basically, just utilize this relationship in both ways, and then you will have the relationship between the two, right? This makes sense, right? Any question about this?
Nope.
Okay, good. All right, let's move on. Let's look at some further calculation here. For example, you have a inkjet head has a drop volume to be 30 picoliter. And then what's the diameter of a droplet having that volumes? So basically, you can consider of one droplet to be a sphere. And then, oh, that's really bad. I cannot draw a straight line. So this is the center of the sphere, and this is the radius, right? And you have the this equation for the sphere volumes, right? Which is 4/3 pi r cubic. R is the radius. What you know is the volumes, which is V, right? And what you want to come up with is this unknown radius. I mean, actually it's diameter, but diameter is twice of the radius. So if you come up with radius, multiply it by 2, then you have a diameter. So basically you want to, you know the volumes, and you want to come up with the radius, and that's what it is. And it turns out it is this amount in terms of the millimeter, and you can convert it to microns. So macron, 1 macron is 1/1000th millimeter. So you can do the conversion of the unit by times 1000 to its millimeter, and turns out it's 38.6 macrons. Another thing you want to be very careful about is this picoliter and liter conversion, right? These are all for the unit conversion, which you need to be very careful, right? Also, you want to convert the liter to be the cubic millimeter, and such that what you have ultimately will be in the unit of millimeter, and finally make it a micron unit. So that's how you can estimate the droplet size in terms of the diameters. But remember, it just is some approximation, because it's not a pure sphere, right? For the droplet. You can just use this to do some estimation only. But sometimes it's accurate enough, especially if you control the droplet velocity, and also considering the viscosity of the material, and make the shape of the droplet close to a sphere, then you can safely use this approximation. Okay, any question about this computation? Okay, good. Another thing is the nozzle pitch versus the normal spacing. So basically, nozzle pitch is the spacing between the nozzles on a printer head. If you ever remember, we talked about this a little bit in the previous lectures, right? We consider this nozzle move in y direction, and this is the x direction. So basically, this is the distance between the two nozzles along the x direction, right? And the nozzle spacing, the drop spacing, is the one along the y direction. It is associated. It is related to the velocity of this printing head motion as well, right? But now let's talk about the distance between each of the nozzle along this direction, which is also called nozzle pitch. So what you could do is you have the dimension of the printing head, and you have the number of the nozzle on one printing head, and it turns out you can easily compute this pitch, right? But for this droplet spacing, that will be different. As you can see here, there will be some patterns like this. Basically, each of the droplet will have some overlap between the previous printed one. And to make sure the material fill the whole region, usually there will be another pass to fill these empty regions. So that's why you have a first pass and a second pass of the scanning to cover the whole region of the printing of the printing surface, right? So as you can see here, the step over sideways has a certain distance, such that the droplet will have will fill these space in another pass. And usually there could be a second pass to fill the region, these empty regions. But in some other unusual cases, that could be third or fourth or even more pass of the prints to further jet more material. So for the droplet spacing, how do the firing frequency and the scan speed affect the drop spacing in the scanning direction? So basically, this will, as you can see, for the spacing between the two, let me clean this up to draw it more clearly. So basically, if we measure the distance between the two droplets, actually it is affected by both the firing frequency, that is how frequent the nozzle generate a droplet, send out a droplet, right? And also the scan speed, that is the motion of the printing head. Both the two will affect the droplet spacing in the scanning direction. And that will be a function of the printing head velocity and the firing frequency. So, and that will be another, just go back to here. And I will show you how to derive it probably in the next lectures. And I will let you guys to think of this and try to come up with your own answer. And we can have some little discussion in next lecture and see how you come up with to think of a function of printing velocity, printing head velocity, and the firing frequency. All right. So let's assume the nozzle, the distance between nozzle and the substrate is 1 millimeter distance. All right, that is what described in the previous slides. Let's fix this for this for the ease of the discussion. All right. So another thing is the printability of the ink. So what is the printability? Basically, that is associated with the fundamental ink properties. For example, the viscosity, surface tension, and inertia. So it describes how easy or how difficult you print using that ink. And basically, for example, the viscosity describes the resistance of an ink to flow through a small diameter nozzle and a very high shear. In that sense, if the viscosity is high, there will be really a large resistance. It will be difficult to jet the droplet onto the printing platform. Another thing is the surface tension. As we mentioned, if the droplet has a low surface tension, it will be elongated. But if it has a high surface tension, the droplet will be more like a spherical shape, right? So that will affect the geometry of the droplet as well as the final geometry accuracy of the prints. And the inertia basically is the resistance of any physical object to any change in its state of motion. And that is the tendency of the object to keep moving in a straight line at certain velocity. And that will also affect the motion of the droplet, especially when it hit on onto the substrate. And again, this will work together with the surface tension to affect the geometry of the droplet and the printing accuracy as well. So I think we can stop here. And in the next class, let's first do a discussion on this droplet spacing by deriving from its printing head velocity and the firing frequency. And then we talk about some other concepts related to the printability of the ink. All right. Any questions before we complete the class? Okay. No. All right. And again, I will follow up with you about the Fusion 360 tutorial. And yeah, just I think you want to move really fast on the project. I mean, it's not safe to work until the last month or last few weeks. Now is the time. I think our semester ends in late April or early March, early May. Let me check the calendar. I think it's early May, right? Just 1 second. Yeah, early May. So I think right now is the time for you to start. You have a full month, full April to design, prototype, and testify the prints. I mean, luckily we have, I mean, fortunately we have really small parts, really small object to print. So that will save time for the prototyping, for the fabrication, but still you want to make it as good as possible to have a higher score. All right. So if you have any questions regarding the project, also let me know. So if you have no more questions, I think that's the end of the class. Thanks for your attention.
I have a question about the
Sure.
project.
Yeah.
You mentioned groups. Are these self-made groups or are these the 4 people we have in our lab sections?
Yeah, I think because as we discussed in previous lectures, it's hard to have the self-made groups because for the very tight plan of the lab schedule. So it's easier to form group just within the the 4 people for the same lab session. So that's the plan.
So it will be groups of 4 then?
Yeah, yeah.
Okay.
Yep.
All right, thank you.
Mhm, mhm.